What if AI could truly understand the physical world, not just simulate it? In this episode, I sit down with Cinnamon Sipper, founder of Godela, an ambitious AI startup building a physics engine that aims to revolutionize engineering and innovation as we know it. From her roots in mechanical engineering to building products at major tech companies, she shares her leap into entrepreneurship, the limitations of current AI, and why Godela could reshape how we design, build, and experiment across industries. Whether you're into engineering, startups, or just curious about the frontier in AI, this one will get your gears turning. Let's get into it. Cinnamon, welcome to Peking. How you doing today?
I'm doing well. Super excited to be talking with you.
Awesome. I am very excited to hear about Godela. When we first talked, you explained it as an incredibly complex product that might be difficult for the average audience. So I'm excited to see if I can understand it. It seems understandable, but before we get there, you've built laptops and iPads for Apple and AI products for Google, and then you decided to build something yourself. Anything from your early career that kind of told you that you did want to make something yourself? How did you get to that point where you were confident in building something yourself?
It's a really good question. I think, well, backing up a little bit, I studied mechanical engineering mainly because it felt like this way to always be learning and always be challenging myself. So much of the degree itself is just learning how to learn and then take those learnings and turn them into like products that people can use that solve problems. And so this whole cycle of identifying a problem, applying your knowledge, and then producing a product that inherently solves a problem is something that is, I think, synergistic to both engineering and entrepreneurship. So they go hand in hand in my eyes. As far as why or at what point I decided that maybe entrepreneurship was a better fit for me, I think it just ended up being that I was really fortunate to get to design products for all these great companies and learn how that process worked. There were just so many interests that I wanted to pursue, and I think it's as silly as I decided I wanted to build products for myself and products that I wanted to see exist in the world.
Absolutely. I think that's an awesome reason to do it. And growing up, obviously you were on a very fast path to greatness getting into Stanford. But before that, did you know that where you wanted to be and what made you pick mechanical?
Yeah, thank you. That's very kind of you. I actually didn't know, um, I didn't know anything about engineering before coming to Stanford. I think a lot of my childhood, I was spending my time playing piano. I thought I was gonna, pursue music until getting into Stanford. And part of part of the draw to mechanical engineering for me was that, like I said, it was this way to continue learning because I felt like there was still so much I didn't understand about the world. Um, and so when I got into Stanford, it was an easy choice because there was so much of this culture of they promote something like they call it intellectual vitality. But to me, it just meant, pursue the things you're interested in, nourish your curiosity, and from there you'll figure it out. And in some ways, mechanical engineering was this way of like, well, I get to go and make up for lost time where I was not really thinking about how the world worked and only was thinking about piano. Now I get to go and figure out and understand how things work, why they work that way, and how I can be a part of that.
What was that term they used to Stanford? Intellectual vitality?
Yeah, intellectual vitality, kind of a fluffy term, means different things to different people, but uh, has a good branding to it in terms of
I
feeling
love
like
it.
it, feeling inspired. Yeah,
I like that a lot more than cracked. All the kids are using cracked now.
that would be something.
That's good. I played the piano up until Fur Elise, and then I stopped there. So as
Hey,
far
that's
as I
good
got.
stuff. That's good stuff. You should keep going.
It is a fun song. Now I have an alto saxophone behind me, but I break it out once a year, and it's a life goal. I set it as a life goal as opposed to like the next 5 years or next 10 years. I'll get to it eventually. I think I don't put time into it right now, but it's such a cool instrument, and music is so awesome. So I
I'm sure your
I'm
neighbors love
glad my
that.
parents introduced me, but they didn't force me into it, which I think a lot of kids experience.
Yeah, yeah. I mean, it's kind of hard because when you're a little kid, how do you know? You don't know the payout of discipline, and so you kind of have to be. I mean, who knows? I think you kind of have to be guided in some way, but yeah,
Yes, yes, absolutely. That's such a great quote there. You don't know the payout of discipline. I mean, even some adults don't know the payout of discipline.
fair
That's
enough.
just like so crucial. Awesome. So let's kind of get into it. So you are building a AI for a 3D physics engine. Is that correct?
Yeah, I think the way you can think about it is it's AI that's capable of reasoning through the physical world. The reason why you would want something like that is because if you think of all of engineering, all of scientific breakthrough, you don't just need to be able to reason through language the way ChatGPT, Gemini, and Claude can, but you need to be able to reason through the world of numbers and equations. And that requires an entirely different class of AI models than what we might be engaging with today. And so we are building a physics foundation model to enable that type of reasoning.
So end result, this would really change every single job that touches any type of CAD software.
I think that's like, I would say that yes, but that's not an end result. I think that's where we start. And the reason being, when you think about the types of problems you can solve with an an AI physics engine, right? To contextualize this, I want to like maybe take a step and explain like the limitations of current AI models, right? If you are an engineer and your job as a mechanical engineer is trying to define and predict how your part is going to behave where it might fail, let's say this laptop they're on, right? You might need to know if I drop this laptop from 1 meter, what is the end result going to be like in terms of the deformation across the case of the laptop? If you ask ChatGPT what happens if I drop this laptop from 1 meter, you're going to get an answer, but that answer isn't physically accurate because the way ChatGPT, a language model, goes about getting that answer is it reasons through the data it's been trained on, which is a mix of language, image, video. But at the end of the day, its method is stochastic at arriving to that answer. Now, I want to contrast this with what an engineer has to be able to do to answer, how will my product fail? Engineers have to rely on equations and computable methods to getting to these types of answers, right? Like the best way to explain this is you have to solve equations, not just like stochastically, like probabilistically guess at the answer. So there's this gap here in which large language models can't resolve physics equations efficiently or accurately. So I'll bring it back full circle, but this new class of physics models, or AI models, physics-informed machine learning models, they're a method in which you can imbue laws of physics into the architecture of the model so that your answers honor physics from the start, right? You're not just getting guesses that look like answers you've been trained on, but you are getting answers that obey physical laws. And only when you have that can you be a useful tool to scientists and engineers who are relying on accuracy and certainty in your answer. Now, just to bring it full circle, what does that mean? It means that for the fields in which people are designing, testing, validating, and trying to understand how the physical world will behave, whether that's a mechanical engineer working on a laptop, a plane, a train, and trying to figure out airflow over my car or deformation as a result of impact. You will be able to ask questions and get answers remarkably fast. I'm talking in seconds, as opposed to waiting for current methods like long simulations or even physical tests. So we can cut out that really clunky, expensive R&D process that everybody relies on today with this new class of intelligence that helps us reason and get answers for those questions that matter.
So there's all these layers with the AI rush. There's the NVIDIA layer, and then there's OpenAI, and then there's all the AI startups that are basically using these models, and some are making their own. You're trying to be somewhat of the OpenAI layer for physics.
Yeah, I think that's super fair. That's a great way to put it. Like there's like foundational like technology and research that goes into the machine learning method that gets you these types of answers that are accurate, and that's a huge body of research. That's the body of research we're in, and I think there are big gaps in the space before the technology is at a point in which it can perform the way like language large language models like ChatGPT perform. But then once you have that, there are applications that can get built on top of that to enable everything from robotic simulations to like traditional, like you mentioned, CAD augmentation to just like experiment replacements, right? Like those are all the applications we think of that are really exciting, but would be built on top of like the foundational technology we're working on.
It seems like an enormous bite to try to chew. What made you confident that you could take on this challenge?
Well, this is our team's expertise. We've been working in, well, our team, where our backgrounds are all in mechanical engineering. My co-founder, prior to this, he was at Intel and he's a researcher, was a researcher at Stanford and Harvard. My background, like I mentioned, also mechanical engineering. And we met TAing a computational mechanics class, which is very relevant because computational mechanics, it's the path by which engineers traditionally get answers to these questions that I was talking about, right? The questions about, you know, how will heat dissipate through my system? Like all the questions regarding physical world, the path to which you get the answers is through numerical computation, and this is what we were teaching. Now, aside of that, our team, our research has been in developing physics-informed machine learning methods that can replace traditional simulation workflows and the traditional tools today. And we've been demonstrating that we can do this for really complex physics systems, whether it's modeling a class of problems like turbulence problems for fluid flow that have traditionally been extremely computationally demanding to resolve, or my co-founder Abhijit, he built a model to capture plasma etching for Intel, so proving that we can model even the most complex physics with these machine learning methods. And now we're thinking about how do we scale that and make it useful to all the other engineers in the space, not just the ones that we get to work with.
Yeah, I mean, one step at a time.
Sure, sure.
Find maybe solve the simplest problems first and see how useful it is for those people solving those problems, and then level up the intensity. So is it a computational problem, like we need just stronger chips? Is it a algorithm? Is it possible that you could write or build a model that's just much more effective and efficient? How are you tackling that?
Yeah, it's a really good question. Like, what is the problem right now that physics foundation model would solve? Is that captured accurately?
That's certainly part of it. Yeah, I'm definitely curious about that. Like, what problem are you solving now? Who are you helping now? And then, if is that the goal to help different professionals in increasing level of complexity as you build?
Yeah, okay. So, and this is like, so I guess one way to put it is like, what problem are we solving? Well, like we've mentioned, every product you've ever used, right? From your phone to an airplane, had to be designed, tested, and validated through a combination of simulation and physical experiments. And those are expensive and time consuming. And we shorten that process dramatically. So we are a replacement to the
Mm-hmm.
simulations and physical experiments. Now, going a layer deeper, how? Well, those if we just start with simulations, right? Right now, simulations, you can think of them as just solving a system of equations, matrix multiplication, that help you resolve how different known physics principles would act on your 3D geometry. And if I want to calculate heat transfer through my laptop or fluid flow over my car, just solving those equations, even with extremely powerful computers, takes a long time. Like the laptop drop simulation that I was talking about, to model that using traditional methods, non-machine learning methods, would take over 2 weeks. Even, and this is what I've seen even at companies where we had access to the most expensive simulation softwares, right? Now, the problem we're solving is we can collapse that to a matter of seconds. So instead of waiting 2 weeks to get a simulation back to know how what's going to happen if I drop this computer from 1 meter, or with model fluid flow over my car driving at 60 miles per hour, right? You can get that on a matter of seconds. So that means you can make real-time design changes, and that the speed of iteration, the speed of innovation is dramatically accelerated. And so that's a huge unlock that we're enabling through our technology.
And what you've accomplished already can, I mean, those are two different problems. Airflow and gravity are, I would think, two different physics problems. You've
Yeah.
solved both with one model. Is that kind of what you're saying?
Oh, this is a great question. So we have part of our pursuit is to learn. Well, first I'll say this is the big challenge. Like, how do you generalize across physics problems, and how do you generalize across problems you haven't seen? In engineering, there are four key domains that capture most of the simulation problem space. We can bucket them into structurals, thermals, fluids, and E&M. And right now, the technology is at a space in which we can train those independently, right? Like those four solvers, we can train independently and solve and bucket your problem into one of those. And what we're working on right now is how do we generalize and cross-link our learnings between those four domains such that with one model or with one process, we can handle both types of problems. So our answer right now is four different models. What we're working towards and what our research is into is how do we tackle those with the same model?
You think that's the right approach as of right now, is to try to generalize the model?
I think in some areas it's a worthwhile learning, and I can share those. So I think we consider it in two ways. One is what does the user feel and experience, and the second is what is worth pursuing just to understand how our technology works and in pursuit of transparency of the model too. So in terms of what the user experiences, my strong belief is it doesn't necessarily matter if it's undergoing one model or an assembly of models on the back end. When you, let's say, as an engineer, ask a question about what is going to happen under these conditions, as long as we can give you a fast, accurate, and interpretable result, that's all that needs to happen in order for you to carry on with your day. Now, from our end, why it is interesting for us to pursue generalizability is because it gives us a better understanding of how the technology works. And it also gives us a better framework for being able to understand how to improve the model. So on our end, behind the scenes, it's this parallel path towards let's deliver the most accurate results possible for the problem you're asking, but let's build that into our larger roadmap of understanding what is the alternative to traditional computational frameworks that a machine learning model could exist as if it truly were able to perform these functions in which it can generalize across different equations and across different problem types, right? Because I think this is what we're chasing. Like, what is the replacement to traditional like computational solvers today that a general purpose machine learning framework could be able to augment?
Does this essentially just make all simulation software obsolete if you figure it out?
And make it all obsolete? I don't think so. I think these things develop hand in hand because different for two reasons. Practically speaking, physics-informed machine learning is we're at the frontier of this technology, right? This is a huge space and growing, and there's a lot of work that needs to be done in order for this field to progress in a place that can truly, quote unquote, replace a method that engineers have trusted and that, $60 billion industry has been built upon. So I don't think like a sweeping replacement is what's coming. I do think it's an acceleration to simulation workflows. It
Mm.
allows engineers to, it speeds up the process uh, by which we can get to the answers that we need to get to faster. And it allows us for the scope of simulation. What this means is it allows simulation to be used more effectively at the problems that simulation is better equipped to handle. And some of the other places where, engineers are just spending hours meshing and iterating through very simple, straightforward physics problems, this unlocks the ability to just cut that time and cut that waste out. Um, and so I do think it's an acceleration of these workflows and not a replacement.
It seems like incredibly impactful technology. It seems like LLMs obviously were as well, and that came through the private sector. Do you have any thoughts on whether or not these things should be, state funded, or whether it definitely is better if the private sector invents this stuff, or should it be done in like a research lab funded by the country?
Well, I think it's I think it's tricky, and I think my answers would be different for the type of model. I'll be honest, this is not something it's a great question. It's not a question that I've thought quite deeply about, but my gut instinct is to say for language models in which the model you're building, the inputs and the biases are so tangibly linked to the training, I think it is more dangerous to have that. Uh, well, maybe we'll just say we have to have more consideration about who owns that model because, right, you could train a language model on a very biased data set and receive very biased outputs, and
Yeah.
and it's very easy for people to trust those results. In some ways, I don't think this is as much of a problem in the same way for physics engines because what you're in pursuit of is more so a sense of truth, right? You're in pursuit of how do parameters impact performance in the physical world. And there's less bias in that conversation. There's less opportunity to skew that in a way that injects your intent or injects, I guess, yeah, bias.
Yeah, no, totally.
Now, the only thing that I will say here that is it, well, not the only thing. One danger though is who has access to this technology as it is incredibly powerful as a tool, not just to be able to um, and democratize access to the ability to a sandbox, an engineering sandbox, effectively. Right? You have a target performance, and we can help you optimize parameters of your design to get there. I think that's powerful technology, and I don't really have an answer for how that should be governed, but I do think we should consider the fact that opening that up will have incredible unlocks for society, but it also means like accelerating all ideas, some we might not agree with as much. So,
Yeah, I mean, it seems like infrastructure. It seems like you're building infrastructure to enable so much more. And if
right,
this
I think that's
does
fair.
actually make so many companies more efficient and so many designers and engineers more efficient, it's like a power up. Then, and it's just needs a ton of research. Then it seems like it would benefit a state to have that research. That's a whole nother debate, obviously.
Right.
So, what are your biggest problems that you're running into right now? What is the biggest challenge for you guys about a year in now?
Yeah, getting access to data is always a challenge. I think that data is crucial for development and it's crucial for delivering accuracy in our models. And I think we're not alone in this, in that as people become increasingly curious about what AI models can do, what patterns you can draw from data, more data is becoming available. But up until this point, the data we've collected, it's been underutilized. Data we as like a society, as engineering companies, as research labs have collected. I think it's been underutilized, and there's just a lot of effort that needs to be put into organizing it, gathering it, and setting it up such that then we can come in and start applying our technology to figure out where are the patterns, what can we predict, and what can we understand about the physical world through this data.
So, you need a scale AI for the physics engine world.
I think so. I think that would unlock a lot for us.
All right, be right back. I'm gonna go start.
Yeah. And you,
It's- I think that's so beyond what I might be able to accomplish.
well, if you
Who
do,
could do
reach out to
that?
me. I'd cut you a check right now. All right. Well, I think folks with general wear, like if you set up like a sensor system and I don't know, it's interesting. I almost wonder if there's a gig economy play for that. Like, there are a lot of folks that are going about their day, going through motions or witnessing motions that are relevant for a lot of physics data collection. I think it'd be neat to see a company outfit like a suite of sensors or like a pack. Who knows? This is not necessarily what I my expertise in terms of
Yeah. How
a
about
business case, but I'd
a
hire you
movement?
guys.
How about a movement to open source all your physics data for all these huge companies that would have a ton of it? Like, and it'll move everybody forward. Everyone will benefit from this. Is
Yeah,
that
this is a great, it is definitely something that we're interested in doing. I think one of our big goals is getting our models to the maturity such that it is useful for us to open source it to folks in a way that it's low touch for people to be able to derive value and to help push this technology forward. Because I really do think it's about expanding the reach of this technology because, like you mentioned, there's just so much impact that you can drive when you don't have to factor in you know, I guess when innovation can happen at the speed of your questions. That's really what we're striving for.
yeah? So you're essentially a research lab. Are you thinking about business at all? Are you thinking about sales at all? Are you just heads down
Not at
working,
all.
or is there someone
Never.
else?
No, of course we are. I mean, I heavily index on the research part of it because I think um there are very meaningful things that need to be aligned in the tech roadmap and the business roadmap in order for you to achieve this grand vision, right? Like balancing those two things is always the challenge. That being said, we are a startup. We do have the pressure to commercialize and make sure that the problems we solve are real, the problems of value. I think what that looks like for us is we work with enterprise customers who have large data sets, big problems to solve, and we prioritize the features that will help them save the most money and the most time in pursuit of their deadlines to ship. And I think that's the most tangible way to start demonstrating that this new class of tooling, this new class of modeling can just help folks reach their business goals that much faster when it comes to building and shipping products.
And you would just kind of license it out, or just like an API for OpenAI.
Well, I think right now we're focusing on select use cases in which we know we can build a solution or apply our solution directly to specific customer problems. Once we get to a point where that's a more repeatable flow, then we would start considering what that looks like in terms of unlocking a self-serve version. But right now it's not through OpenAI. It's, customers work directly with Godela for us to build them a physics model that helps them uh, replace their existing testing and validation or simulation workflows.
Yeah, I understand. I meant like similar to their model of how they monetize their models, essentially.
Yeah, I think
What's next in terms of uh, how do you see this working out? Do you see this as being a do you need way more compute? Do you need more researchers on your team? How do you see the next year going for you?
well, we are expanding the team right now. I think that there's a lot to do, which is great. And so expanding the team to include some more machine learning engineers and software engineers is our number one priority at the moment. As far as what this year looks like, we've got some exciting uh, technology milestones that we're working on validating with commercial applications. That's really what, like, the marriage of those two is really what sets us up well to demonstrate how this is going to be, a generational unlock. So our focus right now is taking these research proof points that we've been developing and commercializing them. And we do that by working closely with select customers who, like I said, while it is important that they derive a lot of value out of us, we're in a unique position in which it's just as important for us to learn from the data they have and the problem they have. And so working closely with them allows us to really develop our technology and our methods in a way that is very meaningful. And at the end of this year, we'll include some exciting releases on our end.
Very cool. I will keep an eye out for those. Does your do you have the same problems as an LLM? Does your model hallucinate? Is that something that happens across all models?
It's interesting. I think I would define hallucination here as like an accuracy. It would be the lack of transparency and inaccurate results. So hallucination would look like answers that aren't physically intuitive or just not accurate to what would happen if you drop, right? And the way that so yes, our models are not perfectly accurate. That was like a fundamental problem. Like, and it's tied to how much data you train on, how quality the data is, but the bigger challenge is, well, how can you be sure when your model is inaccurate? Because even the best simulation tools also can be inaccurate depending on, there's still approximations to some regard, right? So even what we consider ground truth has inaccuracy. The difference, though, the key differentiator is can we trust can we trust the results? Do we know with certainty where the results are accurate and where the results are a little bit more ambiguous and we should go run an additional validation step? So the way we work um, around hallucination in this case is by focusing on providing uncertainty quantifications so that folks know where and which parts of the models they can trust and which parts they might want to go and run an additional validation step on.
Yeah, that makes sense. If you had all the money in the world and all the time in the world, how would you do all this differently, if at all?
Oh, that's a great question. Well, in the world is a really unconstrained problem, but I would say if I had all the money and all the time, the biggest thing that would change is my prioritization of what problem I solve first. Because I think that right now, what it is we're so excited by the technology, but like to your point of you are not just a research, you guys are a startup. That means that okay, we got to blend our progress towards the technology we've got to restructure our roadmap to make sure that it's hitting business milestones, that like this tech milestone also unlocks this business milestone for our customer, right? I think I would structure it a little bit differently if I had infinite time and money, right? Because that would mean we're going to get there regardless. There is no pressure to ship. We're just going to do this for problems that I find most interesting. And I would probably be looking more I'd be looking more like outward at like astrophysics, like problems, things that maybe the immediate draw isn't as lucrative, but there is still very interesting problems to be solved. And we'll get there, but right now we just solve them maybe a little bit more practical problems.
Start building a simulated Dyson sphere.
Maybe, oh my gosh, my co-founder, he's awesome. He wants to be able to, I mean, he wants to be in the astro mining space one day. And so much of what motivates him to be doing this is that uh, when Godela is working in its full capacity, it'll enable him to really quickly be able to design the equipment that he needs in order to get out there and start mining asteroids. So I think problems like that, that's what keeps us excited about the space, that this is going to enable access to like just unprecedented speeds of design and discovery.
Yeah, no kidding. So, in a perfect world, you partner with SpaceX, and they don't have to have all these test launches. You know, their rocket just works because it runs through your model.
Yeah, I think that like use cases like that, once again, I think use cases like that are super exciting. And yeah, so that's, believe it or not, that's like a more practical example. I feel like discovering, I mean, my pursuit is like the universe is computable, right? Like, and I, to a broad extent, um, this is a path for us to peer into that computational result a little bit faster. So those types of, I guess, the more abstract problems is what I would do if there is absolutely infinite time and money. But the SpaceX one is this, believe it or not, and this is great. That's a practical one. It's, hey, right now, you guys are extremely heavy on you skew towards physical testing because that's the fastest way to get you these accurate results as you're trying to push towards these really meaningful breakthroughs. How about we train on your data, give you a model that allows you to replace some of that manual, expensive testing process that instead of, spending millions of dollars in R&D or validation suites, you can get a sense of how your product is going to behave. So this is like the space point.
So we got to get SpaceX's data because they have so much data.
They have
They
tons of data.
track everything that happens.
It's ready to be used. It's ready to be used for them.
It's ready to be used.
It's ready to be
Where
used.
else is this going to impact the economy? What other industries? Does this impact film animation? It impacts, obviously, construction, manufacturing. What are some edge cases of things that someone wouldn't typically imagine it would make an impact that you thought about where else it can really change things?
Great question. I think like the very immediate, like, you know, answers like we've talked about is like simulation workflows, which I think is very exciting, but some people might find a little bit dry. But everything, again, everything we see around us, like everything tangible around us, had to be constructed through physical reasoning. And physical reasoning exists on many different scale degrees. And they're talking about like, yeah, simulation is one part, but this works if our generalizability works the way we hypothesize it should work. And again, a lot of development needs to happen. It means working through physical reasoning even to the most fundamental points, right? It means discovering not just modeling known physics in faster ways, but discovering unknown physics, discovering more accurate representations of how the world works at a fundamental level. Because machine learning, right? It's it is inherently the discovering patterns from data and creating functions of sort to be able to represent those patterns. And so I think in terms of what doesn't seem absolutely relevant now, but is similar in spirit, and this will impact, is when you think about discovery, whether it's drug discovery, materials discovery, these spaces in which understanding how parameters impact performance allows you to invert the problem and say, I want to achieve this performance. What are the parameters? What are the conditions that allow me to achieve that? And that's like that inverse problem, inverse design problem that really will I think will be an exciting time to be alive in and be contributing in.
It's so incredible. The more conversations I have, and I mean, you're kind of at the might be the most complex or not complex, but industry shifting product or company I've talked to so far. Just the more people I talk to, what's coming is just going to be incredible. The people are going to be able to move so fast with if bar nothing terribly happening to Taiwan or something like that. But we need more chips, and hopefully Nvidia continues to dominate and do provide the world with these the processing power for all of this. But it really is incredible to just hear the innovation that's happening in your field and the, the machine learning AI engineers. Just you guys are just in a league of your own, it seems, in changing the world. It doesn't. It seems like that's where all the money is flowing right now, and it seems like it's with good reason. It does. I think some people doubt how things are going to change, but or if they will. I'm so convinced. I think my profession has like a year and a half left, maybe. I think I'm going to get replaced. So we'll see what happens then. But anything else you wanted to discuss, talk about? I think I do have a good understanding of what you're trying to build. I think super interesting conversation
Yeah.
and hopeful to get some potential interest and help build your recruiting profile as well. I'm sure engineers would want to work on such an awesome problem. But anything else you wanted to talk about or discuss?
Well, I mean, just on your last note, like I think like in terms of it's really exciting to be in a space in which progress is moving so quickly. Um, and there is a lot of conversation around like what does this mean broadly for society and what jobs get replaced and who gets cut out and whatnot. I don't know, like maybe I'm extremely naive, but I feel like we always adapt in these cases. Like we as society, we always make room for the things that we want, for the spaces we want to be in. And very similarly to, past trends, I see like Godela and the space of racing through the physical world as allowing the smartest people in the world to create space for the problem, like to be solving the problems they actually want to be solving. So instead of like sitting and spending hours meshing 3D geometries or like iterating through tedious like updates in CAD and tedious simulations, we can put we can put those minds to solving like, really meaningful problems and I think it's maybe it's, yeah, like I said, maybe it's naive. Maybe I'm like just being silly here, but I think it's really exciting for the reason that it's not that we're replacing jobs so much as we're expanding our toolkit to be able to really construct the society that we want. And so that's my rant on that.
I think it's replacing a lot of work that people don't want to be doing, and these technological revolutions have happened many times, and there's always been more jobs as a result, not less. So, there
Yeah.
used to be a lot more people that rode horses. That doesn't happen anymore. There used to be a lot
Yeah.
more people that, push tills in fields, and that doesn't happen much anymore. There's so many more jobs that come out of technological revolutions that aren't replaced. So I'm here for it. I don't want to be behind a computer, 10, 12 hours a day if I don't have to. And, there's other things I'd like to pursue as well. But you got to put money on the, you got to put food on the table. So here we are.
It's true, it's true. No, but it is so neat though, because I just think about, I mean, how now everybody has some level of software engineering ability because of ChatGPT. And now like the whole internet is at not just like a recall point for everyone, but in like a really truly intelligent way. You have like a, almost a PhD level peer to like to be a sounding board and an assistant. And so we want to be that for like the physical world. And so I think, I appreciate you taking the time to chat with me. If any of your listeners, if anyone wants to be a part of this paradigm shift in which we're building a reasoning engine for how the universe works, reach out because we think that this is an inevitable technology, and a lot of the research points that way.
Awesome. I totally agree. Are there active competitors that you're kind of racing against right now?
Absolutely. It's such a and all of them are brilliant. All of them are very exciting to see what they're up to. But I would say PhysicsX, Polymathic, Luminary Cloud. NVIDIA is always releasing different models. There are a medley of startups, incredible ones from YC2. um, Navier is one that comes to mind. Deep Sim. I can go on. And it's all because like
Yeah.
we've just seen so clearly what these what deep learning has been able to unlock for language models for the worlds of like software and coding and image, right? Now just think about if we had that same level of complex reasoning and problem solving, but for understanding the world of like atoms and physics behavior, forces, and I think that's just that truly is like a huge missing piece of this that is going to speed up a lot of change for the better.
Yeah, 100%. Seems inevitable. And I think you're the one to get it done. I'm
Hey,
putting
thanks,
my money
Wyatt.
on you. Where do I sign? I actually have very small angel investor checks available that might be able to buy your team lunch, and that's about it.
Well, let's go. Yeah, if you're ever in San Francisco, I'll take you up on that.
Yeah, San Francisco lunch quite a bit as well,
Yeah, I
more
was
and
gonna
more.
say.
Good deal. Well, thank you so much for coming on. You are definitely an embodiment of the title of my podcast, Peaking, just reaching a pinnacle, trying to go where no one's gone before. Just very impressed and super excited to see the progress y'all have. So thank you so much for coming on. And when you reach certain milestones, would love to have you back and kind of hear about the progress.
Absolutely. Thanks so much, Wyatt. It's a pleasure talking to you.
Likewise. Thank you.